So, welcome back to the second part of the part of speech tagging lecture. So, this is lecture number 8, and in this lecture, we're going to do automatic part of speech tagging using the computer. So, if you want to read and prepare for this week, go to chapters 5.4 to 5.8 in the NLTK book. And as a recapitulation of what we did in the previous lecture, it was we introduced the concept of part of speech tagging and the concept of tag sets. And we also said that we can do this automatically with a machine, with a computer, and that for, let's say, simple languages like English, current state-of-the-art part of speech taggers reach an accuracy of, let's say, between 95 to 98%. And in this lecture, we're going to see whether we can develop our own part of speech tagger and how close it will come to this performance level. Good. So as I said, this is a series of 2 lectures on the task of part of speech tagging and even more general tagging in natural language processing. So the question here is that we follow: how can we automatically tag the words of a text with their word classes? And can we maybe also extend the notion of tagging to other NLP tasks, not only part of speech tagging? And can we maybe so that's also something that you can think about. How can we use and are we able to use the same tool and same approaches for those other tasks as we use for part of speech tagging? So the first question that we have is, how can we automatically tag each word of a text with its word class? Let's assume we have such a text, the back door, and now we are looking for the part of speech tags. Now let's consider the kind of linguistic clues that we may want to take into account when determining the word classes in general. So what kind of linguistic information would we make use of? And here we argue that 3 kinds of information signals would be helpful, namely those based on morphology, those based on syntax, and those based on semantics. And now we will briefly go into all 3. When we talk about morphological clues, we talk about the internal structure of a word. And the internal structure of a word is oftentimes, let's say in simple terms, a sequence of characters, such as the ending of a word, which would be its suffix, or the beginning of a word, which would be its prefix. And those suffixes and prefixes oftentimes give useful clues for the word class of a word. For example, in English, let's consider the word class of nouns. There's a certain very typical endings of nouns, such as nes, ness, ness, or ment, which mark nouns. For example, you have the word happiness, illness, and those are nouns. You have the word government, announcement, and those are also nouns. The linguistic process by which these words have been derived can also be traced back in many cases, like oftentimes when a word ends with ness, it has been derived from an adjective, and then the ending ness has been added to produce the noun, such as in the cases happy to happiness, ill to illness, and in the case of meant, it's oftentimes that a verb has been the origin, and we append to the verb meant to induce the noun, such as govern and government, announce and announcement. For other word classes, we also have linguistic clues. For example, if you take the ending ing, such as running, ending, and saying, you can oftentimes be sure that this is going to be a verb. When we talk about syntactic clues, we talk about the syntactic relation of a word to other words. And this may also be indicative of the word's part of speech. For example, assume that we have already identified nouns. We can use this information as a syntactic clue for finding adjectives. A syntactic criterion for an adjective in English is that it can occur immediately before a noun or immediately following the words be or very. So this is a specific rule for English. In French, you would have different rules. For example, in French, an adjective typically follows a noun, but for English, those rules are reasonable. So let's take this example down here, where we have the word near, and we wonder whether that is going to be an adjective. So if we have already identified the nouns here, and maybe using the last step by taking the morphological clues. Now in this case it's not the case. We have not used the previous morphological clues, but there could be cases where we could use those morphological clues to identify that this is a noun. Then by knowing that we have the adjectives preceding, we could reasonably guess that that is going to be an adjective. And even if we take the whole sequence, we can take the previous two words into account. This is an article which is extremely frequent, so that also would be very easy to tag. So if we have the sequence article, something, noun, so this is there's a high chance that this is going to be an adjective. And also reversely, when we have a thing following, like the copula is, which is a form of to be, or let's say very, this is very close, very nice, we can also reasonably guess that what is following is going to be an adjective. When we talk about semantic clues, we talk about the meaning of a word. And the meaning of a word is also, of course, very indicative of its word class. For example, if we know that something is a person or a place or a thing, a person could be Donald Trump, a place could be Darmstadt, and a thing could be a door. So if we somehow have such kind of knowledge, we can usually guess that that is going to be a noun. Also, if we have further knowledge that something is animate or inanimate, animate would be a human or a cat, inanimate would be a stone, then we also can infer that this is going to be a noun. And for other verb classes, such as for other classes of part of speeches, such as verbs, we may have similar rules. If we know that something can change the state, if something can change the state of something else, then that something is probably going to be a verb. For example, shut the door. So this is going to change the state of the door, right, from being open to being closed. So we could infer that this is going to be a noun. Of course, having this knowledge here prior to part of speech tagging is in some sense unlikely. So it's unlikely that we're going to know first that something is a person without knowing that it's a noun, and then do the induction step or the inference step to the part of speech class. But it could occur, and if we have such knowledge, we could use that knowledge to do part of speech tagging. And down here it says semantic clues are generally hard to formalize, and finding those clues automatically is typically much harder than POS tagging, POS tagging. So this is exactly what I have said. It's unlikely that we're going to have those semantic clues beforehand, because this is even a more difficult problem. So you would rather oftentimes go in the reverse direction. So you know that something is already a noun, and then you can further subcategorize that it is a person, a place, or a thing. Going beyond part of speech tagging, we can also, or like going beyond this standard part of speech tagging that we have done, we can also do other forms of tagging. And one other form of tagging is, for example, morphological tagging. And this morphological tagging means to annotate or to label a word with its morphological features. And the morphological features um, are, for example, whether something is in the singular or plural, the person, and the case. So, for example, in German, we have this very frequently. Da geht sie immer entlang, da gehen sie immer entlang. So, in those two cases, we have the same word, and we also would have the same coarse-grained part of speech tag, namely that this is a pronoun, sie is a pronoun. But if we want to do this more fine-grainedly, we could also say that in this first case, sie is in the nominative, it is third person and it's singular, whereas the second one is in plural, right? So this is a more fine-grained part of speech tagging, which applies to certain word classes such as pronouns, nouns, and verbs and adjectives. Down here is a Turkish example, which I cannot reproduce because I don't speak Turkish, but we have such phenomena in many languages of the world, and some popular ones are German, Turkish, Czech, Latin, Spanish, etc. This morphological tagging is much less relevant for English because English does not have such fine-grained morphological distinctions as those other languages that I have mentioned. We could also do tagging. So people use the word tagging in many different forms, and in its most general sense, tagging means is equivalent, is synonymous to annotating or labeling. So the community in natural language processing has also used this word first in a more restricted sense of meaning part of speech annotations, inferring the part of speech annotation for individual words, but we can go beyond this and even go beyond the fine-grained part of speech tagging to tagging to other linguistic objects, such as the sense numbers. And the sense number would indicate which sense of a word has been used. For example, recall that we had WordNet, and like we saw in WordNet that words are contained in different synsets, and each synset constitutes one word net sense. So we could say here this is the synset number 4, right? So this would also, so we could say, so we could tag each word here where, for its part of speech. In this case, the word form is a noun. We could further tag it for its lemma. So the lemma is the base form. So we could say this is also, it's identical. So in English, it's oftentimes identical. And we could further annotate it with its word sense. So this is the 4th word sense. So in this way, we would disambiguate the different word senses of a word. And if you go to WordNet and read out the definition of sense number 4, it's going to be shape, configuration, contour, conformation, and this is the synset of this word sense. We could also we could do many other forms of tagging. So we could, for example, do some markup labeling of the words in a text. For example, whether that is going to be a directive, so we could label which words should be emphasized if they are going to be a directive to a speech synthesizer. So if we want to emphasize, if we want to, like if somebody speaking pronounces the word big here very strongly, as in the sentence, that is a big car, then we could label this here, or we could tag this here with this emphasis. And similarly, we could tag dialogues um, for well, each turn of a dialogue for its communicative function, whether it's a statement, a question, or something else. So we would have a dialogue here where somebody says, "Dude, I wanted some of that," and then somebody else answers, "Am I missing something?" And then this guy, the first guy, again repeats, I'm gonna go fix food. I'll be back later," etc., etc. And then we could label each sentence here, each dialogue act, with its communicative form. And in fact, there are like almost an infinite number of tagging use cases that you can think of in natural language processing. So, as I've already indicated, we can use the word tagging in a very general sense of just attaching labels to linguistic objects. And now we're going to talk about how can we do part of speech tagging automatically. So we start out with a little bit of preparation. We want to look at the pronoun corpus and get the already tagged sentences. Now, who has tagged the sentences? Most likely that have been human annotators who have done part of speech tagging to each to each sentence and each word in the pronoun corpus. So we import from the NLTK corpus the pronoun corpus, and we apply the method tagged sent and go for the news subcorpus of the pronoun corpus to get the pronoun tagged sense, and then we further get only the sentences without part of speech labels, and these are just the standard pronoun sentences. And if we have the human annotated corpora, then we can use them to later check if our automatic predictions are in fact correct. So the human gold standard, so this is what's called a gold standard, is our reference to which we make the comparison, right? So we evaluate the quality of our automatic tagger by reference to the human gold standard. Now let's go for a couple of more complicated and more refined taggers in different stages. So we start out with a default tagger. And let's say our simplest default tagger, what it's doing is it's assigning the same tag to each token. So this is a baseline, and of course you're going to expect that it's not performing very well because it's linguistically quite stupid, but it can still be an important baseline when you report the quality of your own device tagger. Let's assume your boss or your supervisor or your whatever that could be, your professor is asking you to implement a part of speech tagger, and you come up with a very complicated solution. And then your question, of course, is, and now you say, okay, I get an accuracy of 35%, or like in 35% of the cases my tagger is correct. Now the immediate question would be, how much better is this than a very stupid tagger? And a very stupid tagger is such a tagger that always assigns the same label. And if it's not much better than such a very stupid tagger, then this means, of course, that your design solution is also not very good, right? So this is an important reference point for the quality of your own tagger that you would design. So let's just take the most frequent tag. So what we're gonna do is we're going in the pronoun corpus, and we're gonna check all the so we're going to check all the tags for the words, and we're only keeping the tag, right? So we get just a sequence of tags, and then we make a frequency distribution which tells us, well, verbs occur 10,000 times, and nouns occur 20,000 times, and adjectives occur 5,000 times, etc. And we just take the maximum, and that's going to be a normal noun. So we know that the most frequent tag in our corpus is normal noun, so this is a noun. So we're going to take everything with noun as a very stupid and silly baseline. So we're going to use noun as the most frequent tag, and then we tag everything as noun, and of course you would expect how it looks like. We have a sentence, we tokenize it, we apply our default tagger. So the default tagger that just and this is apparently a standard class in NLTK, and we just say use noun, and then we tag the tokens, and of course everything comes as noun. So now that we have defined our very stupid tagger, let's evaluate it. And evaluation is a critical aspect of natural language processing also. So we want to evaluate the performance of different natural language processing tools. So we want to say, is that outstanding, very good, satisfactory, marginal, unsatisfactory. So this is also evaluation that you will finally receive after having taken the exam in this class. So our idea is we compare the tagger output with the judgments of a human expert, and that's what I've said before. The human gold standard is our reference. And keep in mind that constructing such a reference is very costly because you have to sit down humans and go over the sentences. And of course, how fast can that be? Well, you'd certainly take a few minutes to tag each sentence, and then if you want to tag a very large corpus, it's gonna take a lot of time and a lot of work for humans. And also, humans may not be consistent when tagging 1 million words because they get tired, because they forget about their past decisions. And also, even if one human is entirely perfect in this sense, so if it's entirely self-consistent, the human may not be consistent with other humans. So and this does not only happen between lay people. So you take two people from the street, so to speak, you ask them to do part of speech tagging, they will come up with different solutions. Someone will say this is an adjective, and the other person will say no, this is a verb. But this does not only happen with such lay people, but it even happens with experts. So even experts disagree. And what you would typically do then is you would ask multiple experts and kind of take their majority decisions, or you would, when the majority does not exist, you would ask them to come to an agreement, right? So you would typically use, if there's an unambiguous decision, you would take this unambiguous decision. If there are multiple decisions that the humans are making, you would ask them, you could take the majority, or you could ask them to so you could do both options. You could ask them to take the majority, or you could also ask them to come to an agreement. And in case, as I've said, if the majority does not exist, then of course you would always either draw a random label, which is not a very good solution, or really ask them to discuss this and come to a conclusion. And if we have such multiple experts and we have aggregated them, then this is what we call our gold standard. And then we say that our automatic tagger is correct in for a particular tag decision if it corresponds to the gold standard. So let's do this with the default tagger. So we use the brown corpus as our gold standard. So this has already been created by humans. And then we take our default tagger and we type evaluate on the tagged sentences from the brown corpus, and we get out something which says points 0.1308, etc., with many digits here. And this is what, and the accuracy is, and the evaluation measure that NLTK is using is accuracy. Accuracy means how many of the cases of those words in the brown corpus which are tagged are actually tagged correctly. So let's say you have 1,000 words, and then your accuracy says 130 of those 1,000 words have been tagged correctly. So the accuracy is quite poor. It's only 30% when we recall that we have said in the introduction to this lecture and in the last lecture that state-of-the-art taggers achieve an accuracy of over 95%. So, however, that's no surprise because this is our silly baseline. So in any advanced method should beat this lower bound. So we can call this a lower bound. And the upper bound would be the human consistency, right? And also the default tagger is usually a fallback. So if a more advanced tagger, let's say you come up with a more advanced tagger, and this more advanced tagger takes multiple decisions, and if in a certain case the advanced tagger doesn't know what to do because maybe it's lacking information signals that it would otherwise rely upon, then you can take this default tagger as a fallback. So you would use this tagger then to tag everything as nouns in our case. Okay, let's do a second step of a more intelligent and a more complex tagger, and that one's using regular expressions that we've seen in like one of the previous lectures. So what it's doing is you come up with those regular expressions, and then you assign tokens of the basis of matching patterns. So here are your patterns, and who's going to do those patterns? Well, you have to implement them yourself, or you have to ask a linguist, right? You go to a linguist, or maybe you yourself have some intuition, and you would come up with those regular expressions from the expert, and then you do a match to the text, and if it matches, you assign the word class. So you could say if something ends with ing, and so that's at the end, so I call this a verb and a gerund. If something ends with ed, I call this I label this as VBD. If something ends with OULD, I will say this is a modal, as in should or something, right? And if something has digits, then I label this as cardinal numbers. So you can come up with those rules, but of course, coming up with those cool rules is also costly. That also takes time. For you, and if you change the tag set, you have to adapt the rules, so each new tag sets would come with new rules, and also it doesn't take context into account, so it's just like it doesn't look at the previous word or at the next word as something that we would usually expect, but it just takes at the morphology, it just uses this morphological information, right? So, and here in this case, the patterns are processed in order. The first matching is applied. So if you have two matches, the label is given by the first one in this order here. And the last pattern is the default tag. So note that dot star matches everything. So if you don't know anything else, you just go to our previous decision, which is normal noun, and yeah. So this is the default tagger, so to speak. So how are we going to implement this in NLTK? We take the regx tagger. So NLTK has this as default tagger, obviously. Also, you feed in the tagger, and then you tag the Brown corpus. Let's say you tag sentence number 3, and it would give you this prediction. So it says only is a noun. A is a noun, relative is a noun, handful is a noun, of is a noun, such is a noun, reports is a noun in singular, was is a noun, and you see that really it's not doing very well. So down here it's getting something correct, like this is a verb in gerund, so that seems to be correct, but most other things don't seem to be correct. Then if we evaluate the accuracy, we are unsurprised, given this example here, that the accuracy has gone up only a little bit, from 30% to 20%. Okay, good. So we have seen two taggers that use different information signals. Both of them have not been so very good. Let's look at another tagger. So we take the lookup tagger, and what it's doing, let's say it's taking the first 100 most frequent words in the data set, So you have the Brown corpus, which is already tagged. So you take the first 100, the first 100 most frequent words, because those words usually are gonna be very frequent in new unseen data also, right? And you can assume that like the first 100 words or so, there's some general rules. They would make up 50% of all tokens in a language. So you could already deal with 50% of tokens in a language by just considering the 100 most frequent words, and you store their most likely tag. So if a word, let's say the article the, so you have the article the, and you check if it has multiple part of speech tags in the Brown corpus, and we have last time seen that indeed there will be such ambiguity typically. Uh, you take the part of speech tag that occurs most frequently associated with the article the, and you every new instance of the you annotate with the part of speech tag that is given by the most frequent part of speech tag in the NLT in the Brown corpus. And how are we going to implement this? So we're going to implement this as we take the words from the Brown corpus in the categories news. We make a frequency distribution because we said we wanna get the most frequent words. Then here down here, indeed, we take the most frequent words. We also do we make a conditional frequency distribution of the tagged words in the Brown corpus. And then what we do is we go over our most frequent 100 words. So these are our most frequent 100 words, and we make a dictionary where we assign the word to its most frequent part of speech tag, and we are using this conditional frequency distribution up here, where we have paired the words with their tags. So here is a pairing of words with tags, and then when we type CFD word, we got a distribution for this particular word over its part of speech tags, and we take the maximum out of there, right? And then we implement this as our next baseline tagger. So we type in NLTK unigram tagger, which again is a standardly built-in functionality in NLTK, and we say the model is gonna be this dictionary here, right? It's gonna be this dictionary of the most likely of the likely tags for the most frequent words. And then we're going to do an evaluation, and we see, okay, cool, it's going up to 45%. This is still not good, so it's still very bad, but it's much better than what we had before. And this statement down here says nearly half of a given input text can be handled like this, right? Because that's what I've said. There's this rule that like in different languages, this may be a little bit different, but it's still quite stable, this rule, that the first 100 words make up half of all tokens in a language, roughly. Good. Now let's apply our lookup tagger. So we take a sentence out there, we take the third sentence and we tag, and we're gonna see only a relative handful of. So we see a is like attribute of is a preposition, so that's gonna be correct. But you see that here still it makes quite a few mistakes, right? Only has been tagged as none because it's not one of the most frequent words. So how can we handle those other words? So there are two options that we can do. The first one is we can just go back to the default tagger, which tagged everything as a noun, as an NN. So we can back off. So in NLP terms, this is referred to as back off, right? So we have our more complex tagger, and if it doesn't know what to do, we back off to something simpler. And how you can implement this in NLTK is you take the unigram tagger, you take its model, which we said would be the most likely tags, and then you take the bag of tagger, and this is going to be the default tagger. So this would label, this new baseline tagger would then label those unknown words here with NN, right? Good. Now the next option that you can do is, we said you can only take the most frequent 100 words. So we said here the most frequent 100 words, right? Now this 100 is actually a parameter. Instead of going for 100, you can take 200, 300, 400, 500. And what is going to happen when you take the most n100? And let us see this with a small illustration. Okay, and this small illustration here, let's make this bigger, and I'll show you what I've actually implemented. So so this is, again, I'm on a Linux shell. I'm on a Linux server, and I have my Linux shell here, and I have basically implemented what we've seen here as a function, what we've seen on the slides as a functionality. So I said I called this I implemented this function my baseline, and it takes one argument, and the argument is n, the first n100 words, the most frequent n100 words, or the most frequent n words, right? Before it was 100 words, now we make this a parameter and set this to n. So I basically use the same implementation as you've seen, and then do the evaluation, right? And then here I give you some small other details of what I'm doing here. Is I say, okay, if we're, so this is just the main program, so here's where the program starts, and this is functionality. That's how you do it in Python. That's how you can do it in Python if you haven't seen that before. You just put up your functions and your classes up here, and then you run the main program. And this main program takes an integer n from the command line. So in Linux or also in Mac, you can specify the command line, and you do this by importing the sys the sys module, and you say, give me the argument variable number 1, and you put this into the command line, and I'll just show you in a second how that works. And this integer converts this from a string to an integer, and then you pass this n to the function myBaseline as an argument, and this returns an accuracy with like 10 different digits. And here I told it to restrict this to the first 4 digits, right, for better readability. And that's also what you should use. Don't show 12 digits, because the last digits don't matter at all. So what matters is only the initial digits in a floating number. And now we run this program, and we had before the first 100 sentences, and here again you can see what happens when we take the first 100. So this repeats the 45% accuracy. Now we double to 200, and we're getting an accuracy of 50. Now let's double again, so we're getting an accuracy then of 56. Let's again double. We're gonna go to 63. Let's double again, and then we are at 70. So what you see is the more words we take into account, then we go to 78, and then we can double again, and we go to 85, and let's double one last time, 12,800, and you will see that we go above 90%. So we have seen a nice and decent improvement by just considering more words in our brown corpus. So what it's doing now, it knows the most frequent 1280 words and their most frequent tag, and it it tags each word with this most frequent tag. So we don't have very many words for which we have. So we have very few words for which we actually do not know the decision, and those few words are those words that are not the most frequent 1280 words in the Brown corpus. And this, the illustration of this is exactly what we see in the figure here, namely as you increase the complex. So we can state this more abstractly as saying if you increase the complexity of your model, which you can also denote by the term model size. So if you make a bigger model, you typically get such a pattern where your performance increases, but this is oftentimes it's such a concave function where even if so your increases decrease, right? So when you go from 100 to from 0 to 2000, you see a steep increase, right? In the beginning you see a steep increase, but then as you add more and more, the increases reduces. So to get a better performance, you need to input many more parameters, right? So overall, this is a classical performance curve that you will see in automatic NLP systems. Okay, we can also implement this unigram tagger more simply. So now this is exactly the same tagger, but it's just done more simply using built-in functionality of NLTK, and we can, when we use this, we can omit or we can abandon and reject this frequency dist methodology. So we just would say the unigram tagger with the Brown tagged sentences as the model. So we feed this as the model in, and it would automatically take all the words without any frequency restriction. And then we can apply this tagger to, let's say, the Brown sentence number 2007, and we would see something like this, and at least the initial words look promising. And then we evaluate our tagger and we find it has an accuracy of 93%. So now we are very happy because the accuracy has increased a lot. So there are now two questions. The first question is, why are we not at 100%? Because we are actually, so we take the tagged corpus and then we also evaluate on the same corpus. So we actually have the full information, so why not 100%? But of course, you know, it's not 100% because we have this silly model of just taking the most frequent the most frequent label, right? So there is ambiguity, as we have seen in the previous lecture. So multiple words have multiple tags, and we discard this ambiguity here by just focusing on the most frequent tags. So we don't get 100%, but only 93%. And then the other issue that we have is why is this number here, 93%, actually not a good estimate of the actual performance of the tagger? And this is because so in machine learning terms and also in natural language processing terms, we have the same test data as our training data. So this up here is called our training data. So the tagged sentences, because we feed them, what we feed into the unigram tagger here, this is our training data. We take the statistics from this data to infer our tagger, and then we apply it on the same data again. So this is not what we're going to have in reality. In reality, we have the Brown corpus, and then we're going to use it to tag something else. We're going to use it to tag Twitter, for example, or we're going to use it to tag not the news subcorpus of Brown, but another subcorpus of Brown, right? So that's what we're going to use in practice, and we want to estimate how well would our tagger perform in reality, in practice, in the wild, so to speak. So we need to change this. We need to change the training set and the test set. They need to be different. And how people are doing this in machine learning and in natural language processing is that they separate training and test data. So when training on some data, we must not test on the same data. So this is extremely important for you to keep in mind. And if you train and test on the same data, you're making a huge mistake, and your boss, your professor, your supervisor, they will be very unhappy with you because you make a huge mistake, and a very basic mistake also, that totally inflates your performance scores. So the goal in machine learning is that we want to have an estimate of the performance and on new and unseen test data. So we could just take a different corpus. So we could say we train on the news corpus of Brown and we test on another subcorpus. That would be a good option. But often we don't have such multiple corpora available. So an easier way to do is to just split the existing data in splits of, let's say, 90% or 10%. Or of course, you can also use other splits if you have very little data. So for example, you could use 50-50 or 75-25. This really is also a matter of your available data. Let's say if you have very little data available and 10% of that are just 10 sentences, then you will also get a very unreliable estimate, because 10 sentences is not a good quantity, is not an adequate quantity to get reliable statistics from. So you would increase this number in case of little data. Okay, so how would we do it in practice? We take 10% of the data. So 10% or 90%, we take 90% of the data. These are 4,000 sentences. Then we take the training sentences. These are the first 4,000, and the test sentences are the last ones. So that's the remainder. So that's a few hundred sentences. Then we train our unigram tagger on the training sentences and evaluate it on the test sentences, and you see it goes down to 81%. So the performance is worse. So maybe you may have the impression that you make your supervisor or your boss less happy, but it gives a much more realistic picture of what you will see in real data, right? So this is the correct number. The 93% were the false number. And here also something that you should keep in mind is, don't take the first 4,000 sentences in reality. Do a random shuffling of your sentences, because if you take the first 4,000 sentences and the last few hundred sentences, there may be some systematic patterns. Maybe the last few hundred sentences are much simpler because they are just a list of names or something. So you would test on something which is maybe very simple, or maybe it's very difficult also, right? But it could have particular characteristics, and maybe you don't want to have those undesirable or those particular characteristics you don't want to necessarily evaluate on them, but you want to see what happens on a random set of sentences, because this random set of sentences is likely going to be much more representative of the real data that you're going to evaluate on. So do a random shuffling in reality. But still, a takeaway message here is we're at 81% and we're still not happy with this. So what can we do next? So now let us generalize the unigram tagging that we've seen. So unigram tagging, what it's doing, it just takes the current word. So this is a sentence with its tokens. So we have the current token here, WN, and when we want to determine its part of speech label, we only check this word here, right? So we would get the most frequent word for this, the most frequent tag for this part of speech label, and then give it this tag. So this is, in a sense, is not very clever, because we have seen before that to determine the part of speech, context is essential. And in essence, in natural language processing, context is always essential. We have seen that there's a lot of ambiguity in natural language processing. That's what makes natural language processing difficult. And to disambiguate the ambiguity, we need context, and the context is doing this thing. It's disambiguating. So so what we could do instead, and to make an illustration of this for the case of part of speech tagging, that's one example that we've seen earlier. Namely, you would say that oftentimes the part of speech label for a word depends on let's say the immediately preceding word, or the let's say the two preceding word. And we can make an example with the word can, C-A-N. So I give you two contexts. The first context is I can do this, and the second context is this is a tiny rusty can. And in both cases you see that the context, if you have a pronoun in front of can, then it's much more likely that this is going to be a verb. And on the other hand, if you have an adjective or an article in front of the word can, then it's most likely going to be a noun. So the context is disambiguating, and the context is giving useful information, and we can generalize unigram tagging to so-called n-gram tagging, where we consider the n-1 preceding tags. We could also consider the n-1 preceding words, but for simplicity, let's assume we instead have access to the n-1 preceding tags. And in case of 1, if n is 1, so this is unigram tagging, we have 0 preceding tags, so we only take the current word into account. If n is 2, we have the current word plus the previous part of speech tag, right? And we are tagging sequentially, so once we've tagged the first word, we know it's part of speech label. Then for the second word, we know the word itself and the previous part of speech label, so we can also assign a tag here. Okay, so I'm not going to go into implementation details of the bigram tagger. So bigram is the case of n equals 2. That's the simplest generalization of a unigram tagger. So I'm not going to go into the implementation detail, but I'm showing you the standard implementation of NLTK, and we're going to do a little bit of evaluation. So we're going to now set up the bigram tagger as a standard module in NLTK. We're giving it the training sentences, and then we want to tag an unseen test sentence. Let's say the sentence number 4203, and we're going to tag this unseen test sentence. In general, we're going to do a full evaluation, and we see that it has only 10% accuracy. Now, where does that come from? Now, we have a more complex model, but it's performing actually worse. So this seems to be counterintuitive. But let's look into this one example here. So first, it's doing reasonable. It's saying population is a noun, off is a preposition, Congo is a noun. Okay, and then you see it's assigning a label to is. I am not exactly sure what this label is doing here, but then here it's seeing something that it cannot deal with, because it cannot deal with it because maybe 13.5 has never been in its training data. So this is something that is encountering new in the novel test data. So it cannot tag this instance, so it's giving it a none. So now in the training data, it has never ever seen none, because none was just not there in the training data, because everything had a label in the training data. So now what it's doing from then on, it's labeling because it's never seen none, so it does not see the case of million and the previous label being none. So it's continuing to tag none because it has never seen those condition in the training data. And that's why its performance is decreasing so dramatically. So now we have a big problem. Well, and this phenomenon of not having seen enough instances is a general pervasive problem in NLP, which also goes by the name of data sparsity. And it's also a general problem in machine learning. And it generally means the larger we make our context, the n here, the fewer instances do we observe, right? So we may see many instances of nouns, but we see fewer instances of adjective nouns, because this is a real subset of the cases where we have only nouns. And we have even fewer instances of preposition, adjective, noun, right? The larger the context we make, the fewer instances we observe. So this means our coverage decreases. We don't cover all of those phenomena in our training data sets. Because our training data sets are also just, they're also just limited, right? And this is really a huge problem in machine learning, and this is the reason here why the model, even though it seems to be more complex and more powerful, it actually performs worse in practice. So what can we do to alleviate this data sparsity issue? Well, we do this back-off strategy, and this helps us to deal with the data sparsity. So we first start out with the bigram tagger, which is our most powerful tagger, and we say that it should back off to something less powerful in case it has not observed a certain bigram in the training data, right? So once some phenomenon has not been covered by the training data, then it should back off. And it backs off to a unigram tagger, which is seeing more phenomena in the data, but is a less powerful model overall. And then finally, the unigram tagger, if that doesn't know what to do, because maybe it also has not seen a certain word in the training data, then it backs off to an even simpler tagger, namely the tagger that labels everything as noun. And keep in mind here that it could also back off to our regular expression tagger that did take the morphology of words into account, and this probably would even be a better back-off strategy. And now if we evaluate this new tagger here, which is a combination of of subsequently less powerful taggers, we see a new performance increase. Namely, we go from 81%, which we had with the unigram tagger, to 84%. And this really tells us that now including this bigram tagger and properly including it with a backup strategy really helped us to solve some problems that the unigram tagger could not solve. So having context matters. Good. So now a final question here is if we have contexts that have been seen only once or twice, then maybe we can discard them. And why can we discard them? Because maybe those are gonna be very unlikely to appear in the test data, because if they were there only once or twice, maybe they are some very rare phenomena, and maybe making statistics from those one or two can be misleading, right? Because they are rare phenomena. Maybe they have been mistagged also by the humans. Maybe if we have such low statistical evidence, maybe it is better to trust the unigram tagger instead of the bigram tagger that relies on very low statistical evidence. And you can check yourself if this cutoff does indeed help something. Good. Finally, we go a little bit into something which is also very important and often underestimated by students, namely error analysis. And the error analysis is important to find cases where your model fails, and this analysis can then help you to improve your model. And what is very common is a so-called confusion matrix. So this confusion matrix is it's a symmetric matrix. It has m by m elements, where m is the number of part-of-speech tags. So in English, let's say we have 12 or 20 or 30 part-of-speech tags, depending on our part-of-speech tag. So it's going to be a 12 by 12, 20 by 20, or 30 by 30 matrix. And the rows or the columns, so that depends on the definitions. Let's say the rows correspond to the correct text, so we would say um, so this is the tag that should have occurred, let's say a noun or a pronoun or a verb or something, and the column corresponds to what your tagger is doing. Let's say it should have said noun, but it's saying something else here, right? And it should have said adverb, but it's saying adverb in only 4% of the cases, and in 2% of the cases instead it's saying that it's a noun, right? So this tells you what your tagger is confusing the individual part of speech tags with. And each cell, so each entry in the matrix, contains the number of times tag row, tag noun was classified, tag adverb, so this is the row, tag adverb was classified as tag noun, and the number of times that tag adverb was classified as adverb, right? And the diagonal elements correspond to the correct classifications, and off-diagonal elements correspond to misclassifications. Now in this case here we have a percentage number. I'm not really sure if that's supposed to be a percentage number. I think this is just a formatting issue. I think this should be absolute numbers in here, and this indeed, so as I said, it's helpful for you to find out what is your model confusing things with, and it's reasonable to assume, for example, so NP stands for noun proper, so that's a proper noun, that's like Angela Merkel, so it's reasonable to assume that it confuses proper nouns with nouns because those two instances are actually also from a human perspective very similar. And if you go not for a confusion matrix but for a hard metrics such as accuracy, keep in mind that they are often hard to interpret. So some people say, so they're like simplistic assumptions and naive assumptions, especially from practitioners that say like you need to have 90%, so that sounds really good, 90%. If you have 90%, that's cool. But instead what you should compare to is the lower bound and the upper bound. So if the human upper bound is 70%, and there are problems that are really difficult also, and or maybe especially for humans, you cannot expect that your system has 90%. You should expect that your system has, or your system would be considered nowadays still excellent or very good if it has 65 or 60%, right? If in contrast the lower bound, a very simple baseline, has 89%, then having 90% is not a good performance. So what you should do for a good evaluation is that you locate your system performance between those lower and upper bounds. Good. A final word in the context of our simple taggers is how do we store them? Let's assume you train on large corpora, and that takes a lot of time. So training could take hours or days. So you don't want to repeat that. So once the training is complete, we should store the training parameters into a file. So you store that to disk, because maybe disk space, you have a lot of disk space, but you don't want to repeat a 3-day training. So you can store that using Pickle. And if you don't know what Pickle is, check it up on the internet or check in the tutorial. It's well, in short, it's a Python functionality that allows you to efficiently store objects. So you would say from Pickle import dump, then you open a file that you give the ending Pickle, and you say you want to write into this file. You store your tagger into the output, and then you close everything. And once you have done that, then maybe a week later, or a year later, or some months later, you decide to load your tagger again, So you import the load functionality, you open this same file, but this time in read mode, so don't overwrite it, and you load your tagger, and then you can reuse your tagger. So, and let me finally wrap up with some excursion to neural networks as in some other previous lectures. So what I've indicated to you a couple of times in this lecture already is that the current state of the art is very far away from the techniques that we are learning in this introductory lecture. So people, almost nobody nowadays who is doing research on those topics is using those engram, those simplistic engram taggers with backoff that we have seen in this lecture. Instead, what people are using is they're using neural networks, and especially they're using so-called recurrent neural networks, and they use a particular variant of that, namely long short-term memory networks, also referred to or also abbreviated as LSTMs. And note, this is even by 2020, those network architecture is even outdated and has become replaced now by so-called transformer networks, but which I cannot or I will not explain here, not even in brief. But let me quickly explain the RNN, the recurrent neural network architecture, to you, just so that you get some idea of what is going on in practice. So what it's doing is here, we have a sentence as input, it was an awesome movie. And it would first, we would represent each token in this sentence by a word vector. And we have seen these word vectors already in the lecture about synsets and lexical resources and WordNet. So this was the lecture where I briefly introduced those vectors. And it's important that those vectors are informed only by plain text data. So we don't need any annotations, any human labels, but we just do plain text data in the English language, for example, and we try to predict the context. So we try to predict an auxiliary unsupervised, what is called unsupervised task, namely to predict the context, and we use the vectors that so first we induce for each word a vector, and from this vector we try to predict the context, and then after the task has been completed, namely to predict the context, we only keep those vectors that come out. And the intuition is that context is important for semantics, so our vectors should be informed by semantics. And also important is that if two words are similar, that is, they have the same context by definition, then they are semantically similar, then they should get the same vector representation. And this is what we're using here. We use those static vectors that we have trained on some corpus, on some very, very big corpus, such as Wikipedia, as initialization. Then we feed this into another layer of our network. So this is a vector, this is a vector, and this is a vector. And we get some hidden representation. So basically this hidden representation is summarizing the input here. And at later time steps, so this is time step number 1, time step number 2, time step number 3. At later time steps, you see this is, you have this hidden state vector is informed by the input, but it's also informed by the previous hidden state vector. So that means there is a recurrence equation between those two. So recurrence means it's going back onto itself, right? So it's taking the previous object of the same quality, namely also a hidden state vector, into account. And this previous hidden state vector again is informed by the one preceding it. So when we are here, we actually have the complete history. So we know about all the previous input words once we are here, right? So we know what has come in, at least in principle. And then we make the decision to say that this is an article. And here, like the tag set is written in more intuitively understandable, in a more intuitively understandable manner. And then we predict that this is an article. And again, it's going to be a vector that we are predicting, and this vector has the size of this output vector here has the size of the tag set. So if our tag set has 30 labels, we have a output vector of size 30. Okay, so this is one state-of-the-art architecture that has been used. Importantly, compared to our n-gram model here, it is not taking the previous labels into account, so it makes a deviation here, even though there are modifications that could also account for this. But instead, it's taking the context on the input word side into account. And it's not limiting it to the previous n, but it's taking an infinite context into account by having this recurrence relation here. Okay? So it can take infinite context into account to make its decision, and this is obviously a good thing because, as I have repeatedly argued, part of speech tagging and other natural language processing tasks crucially depend on context. And if you want to just get a mathematical impression of what's going on, I will not go into that, or this is not like a core topic, or like this will not be relevant for the exam, but just that so that you get an an impression of what will be awaiting you if you take the Deep Learning for NLP course in the summer semester 2021. So you're gonna see such equations, and basically you see that part of speech tagging becomes or is translated in pure mathematical equations in terms of matrix vector multiplication. So just to give you a short impression of what's that, so this xt is the word vector at time step t. We're going to multiply this by a matrix U. We're adding to this the previous hidden state vector, so that is the previous hidden state vector multiplied by a matrix W, and then we're going to add another set of another vector to this equation. We're going to get as output a vector. We're feeding this into something which is called a nonlinearity. So this is some that's also called an activation function. So we have a linear model here, and with this activation function on nonlinearity, we're going to make it nonlinear. We get the ht vector. This is this vector. Then we are multiplying this vector again by a matrix V. We've got again adding some linear term to that. So we're going to get another vector OT, and then we're going to apply another nonlinearity. In this case, it's called softmax nonlinearity to this to get our final output prediction, YT, and this output prediction then leads us to one class label. In this case, it would be article. Okay, so this is the math behind it. So basically, if we have such an approach, then linguistics and natural language processing translates into pure mathematical operations, which some people, especially those that are more affine to mathematics, appreciate very much. So the take-home message from our whole lecture number 8 is we have done automatic part of speech tagging. We have seen that it's informed by morphological, syntactic, and semantic clues. And note that we have said morphological and syntactic clues are maybe easier to leverage, but semantic clues are harder to take into account. But now in this last 2 slides that I've shown you, I've said we could also use those word vectors, and those word vectors are actually informed by semantics. So they capture semantics. So this would also be a form of semantic clue. We have seen different tagger variants, from baseline taggers to more complicated taggers. In particular, we have seen n-gram tagging and some tagging examples, what can go wrong, what can go well. We have seen the experimental setup to split in train and test set and do an evaluation, and how you have to do it properly. So you always have to take train and test into account. We have seen that more complex taggers do not always work better, and you have to have, if you use tagging paradigm that we've introduced, you need to do something which we call bag off, and it's useful because it's relevant in many different applications. For example, speech synthesis. If you want the computer to pronounce words correctly, then you need also be knowledgeable about the part of speech of those words. For example, nouns and verbs usually have a stronger accentuation compared to function words such as prepositions. It's also important, let's say, for information retrieval. Let's say you're searching for a book. You're searching for your favorite book. So you should also know about books. So when you type into Google or your other favorite search engine book, you would also want to take into account, let's say, adventure book. You would also want to take into account adventure books. So it would retrieve documents that are in books, but you do not want to find it travel documents such as to book a hotel. So you would hope or assume maybe that Google is part of speech tagging those documents for you, and when you type in a search query, it maybe knows about the part of speech of your search query, and it matches this to the document. So it does not only take the word form into account, but also it's part of speech tags. It can also be important for word sense disambiguation and lexical substitution. Let's assume you want to paraphrase a sentence, because that is often relevant if you do if you want to have sophisticated writing that is not repetitive, for example. So you want to paraphrase something. So you would paraphrase to book a hotel into to reserve a hotel, and for this you might also, if you do it automatically, it might also be very helpful if you know about the part of speech of the word book to find adequate substitutions, namely only such substitutions which indeed are verbs. Here are several links, how to do part of speech tagging with NLTK, another lecture on part of speech tagging. So here's like TNT, that's a paper on a very old, very old statistical parser, and another very old paper on part of speech tagging. So these are all very useful and really constitute important background, but keep in mind that these are super old and super far away from the state of the art. If you want to check out tagging performance in English, you can go to this page here, which gives you the state of the art for English, and keep in mind that for English this task is actually solved. Part of speech taggers nowadays perform on the same level as human experts. So part of speech tagging in English is a solved task. This does not necessarily hold for other languages. It does also not hold, let's say, for more fine-grained part of speech tagging. We've seen this morphological tagging is much more fine-grained. So here, computer performance is still below human performance, and it may also not apply to other forms of tagging that we have seen, right? We have said that the word tagging can also be used more generally to refer to annotating linguistic objects, and of course, depending on the difficulty of the task, we may still be very far away from human performance, such as in argumentation tagging, and there also you need to tag text, but with argumentation labels, like the argumentative role of a piece of text, and this is still a very complicated and tough task for the computer still nowadays. If you want to prepare for next week, recapture what we've done today, go to the practice class, and feel free to consult the NLTK book in chapter 6.1 to 6.3.